So using the logarithmic properties and the derivative of logarithm, here is a very powerful differentiation technique. It's called logarithmic differentiation. It goes like this. Actually, I might as well start with an example here. So this will be logarithmic differentiation. So we call it example 1 because even though we are within the same section, it's more application here. Here's some extremely ugly looking function. Looks like that. Probably shouldn't have used the word ugly. I'm hurting this function's feeling. But it looks like this. You have, it's a rational or some kind of rational function. You have x raised to the power of 3/4 times the square root of x squared plus 1 divided by 3x plus 2 raised to the 5th power. Okay? You want me to add to that some stuff? Nah. Let's find the derivative y prime. So I don't know about you, but I'm looking at this and I say, oh my goodness, this is a tough one, isn't it? Product rule, product rule, quotient rule, you name it. But here's the beauty. This is an equation, basically. We have y on one side and something else on the other side. And we already know how to do implicit differentiation, right? So we know that we can differentiate both sides. But when you talk about logarithmic property, if you have one side equal to the other side, for instance, a equal b, we also know that the natural log of a also equals natural log of b. Or if you have a equals b, then e to the power of a also equals e to the power of b. Okay, so we'll use that. We're going to apply the natural log to both sides. And see what happened. Okay, so on the left side we'll have the natural log of y. On the right side we're going to have the natural log of this cluster. But we have a product and we have a quotient. And I'm looking to my left and I say, okay, on the left, on the right side, I can write it as the natural log of x to the 3/4. Since I have a product to the plus, the natural log of the square root of x squared plus 1. And then since I divide, then I have minus the natural log of 3x plus 2 to the 5th power. So that looks already better, right? But we are not done yet, because I have property number 3 available to me. So continue here, we have the natural log of y on the left. We'll deal with it later on, but it will be 3/4 natural log of x, right? Square root is the power of 1/2. We saw it in the previous example, so we'll have plus 1/2 natural log of x squared plus 1. And of course, minus 5 natural log of 3x plus 2. And I think we are pretty much ready to take the derivative now on both sides. So, implicit differentiation now, right? Because we're going to take the derivative of a function containing y. So, what is the derivative of the natural log of y? Well, it will be 1 over y and then dy dx, so we'll call it y prime. And now we take the derivative term by term here. The derivative of natural log of x is 1 over x, so we have 3/4 times 1 over x. And then plus 1/2 the derivative of this one, right? So the derivative of the natural log of x squared plus 1 will be 1 over x squared plus 1, but then we need to take the derivative of x squared, which is 2x, and that will be on top. So the 2x and the 1/2, the 2 on top and the 1/2 are going to reduce each other. And then we have -5, again 1 over 3x minus 2, but then the derivative of 3x is 3. So let's bring it home now and finish this exercise. So we have 3 over 4x, and then plus x over x squared plus 1, and minus 15 over 3x minus 2. But this is only y prime. Only y prime over y. This is not the solution. We need to find dy dx, or y prime. So y prime will be everything, all of this multiplied by y. Okay, so it will be 3 over 4x plus x over x squared plus 1 minus 15 over 3x minus 2, everything multiplied by y. Remember what was y? Y. It was that function we started with. And the function we started with was x to the 3/4 times the square root of x squared plus 1 divided by 3x plus 2. Is it plus 2 or minus 2? Plus 2? Let me look at the original function. Plus 2 somehow. So 3x plus 2 to the 5th power. And that is the answer. You can see that logarithmic differentiation allows you to solve quite complex functions, or find the derivative of rather complex functions.